Are we live? Looks like we're live. We're live. All right, so Lewis structures. Lewis structures are a way of visualizing molecules. Okay? So they start with the simplest thing there. There we got the Lewis symbol. Okay? So the Lewis symbol, you just take the atom and you surround it with the appropriate number of electrons. So we open up this guy right here. Okay, so we have our periodic table. So all we care about is the number of valence electrons. We don't give a darn about anything else going on there. Okay. So for example, sodium, element number 11, way over here on the left, alkali metal, only has one valence electron. So when we draw out the Lewis symbol for sodium, we draw it as just sodium with a dot. And that dot represents its single valence electron. Meanwhile, we come way over here on the right side of the periodic table to carbon. Carbon is in the second column of the p block, so it has 2 s electrons and 2 p electrons. So carbon is that. Or that. You can draw it sort of either way. This way is a little bit more honest because it shows the 2 s electrons paired up and the 2 p electrons unpaired. But when it comes to carbon forming bonds, it will tend to form 4 bonds because it has 4 valence electrons. So it is usually more useful to draw it that way. In any event, we come all the way over to the right, well, almost all the way, over to fluorine. Fluorine has 7 valence electrons. So fluorine, no matter what, is going to be 1, 2, 3, 4, 5, 6, 7. No matter what you do, most of its electrons are paired up. It only has the 1 unpaired electron. That's why this is, more honest, more accurate to show carbon this way. But the fact is, you're never really going to find a carbon atom by itself. It's either going to be it's always going to be part of a molecule. Even as in its native elemental state, it's going to be part of diamond or graphite. In any event, this is how we draw the Lewis structure. Notice that I've made it a point to try and, at the very least, make them small circles. If you're writing with a pen or a pencil, you'll definitely want to do that because otherwise it'll be easy to lose track of them. These would just be dots otherwise. And did you mean to draw that dot or not? It's hard to tell. So go ahead and make them deliberate, make them more visible. Now, from here, we can go on to draw the Lewis symbols for ions just as easily as anything else. So, for example, sodium, in order to become an ion, it will lose its only electron. So you would just be left with sodium 1+. Okay. And to draw ions, we typically put brackets around them and then put the charge outside the brackets. Meanwhile, carbon is going to gain 4 electrons. So one way, this is not really an official way to do that, but you could try and indicate them as being somehow different to show that carbon has gained those 4 electrons. And once again, we put the brackets around it and say that it is carbon 4- because it's gained 4 electrons. Then we come down here to fluorine, and we indicate that it has become fluoride by showing that it has gained an electron. And again, I want to stress that this little X being a slightly different electron is not an official kind of thing in any way, shape, or form. We mostly just represent electrons with dots. All right, and still we put brackets around it and give it a negative charge. Okay. So those are Lewis symbols. You just surround the atomic symbol with the appropriate number of electrons, whether it is a neutral atom or an ion. Obviously, this would get a little bit more complicated if we were to do anything with the D block transition metals, because we're dealing with d electrons. This really works best with S and P block, main group elements, when we're just working with that noble octet, the stable octet, those 8 electrons that you learned about once upon a time. Now, let's go ahead and move on to Lewis structures. How can we use this to work out molecules? Well, there is a set of rules that we can use. This will come back into focus in a minute, never fear. Dang it. I would have had just enough room if I hadn't screwed up. All right, so 6. All right, so these are the 6 rules that we use to sketch out Lewis structures. There will be one atom at the center of our molecule. Okay, so I go ahead and I call that the core atom, and the atoms around that I call satellites. Again, these are not official terms. I just needed some way to be able to distinguish them. Then we're going to count up all of our available electrons. This will be the pool of electrons that we use to make up all of our bonds and all of our lone pairs. Okay. Don't forget to subtract the charge on your molecule. If you have a positive charge, that means you have fewer electrons available. If you have a negative charge, you have more electrons available. So you just take your pool of electrons, you subtract the charge. Now, this pool of electrons is just the valence electrons from each of your atoms. Okay, so carbon has 4, oxygen has 6. So carbon dioxide has 4 plus 6 plus 6 is a total of 16 electrons. All right. Then you draw a single bond from the core to each satellite, and each bond is going to use 2 electrons. Then you fill in the octet on each of your satellites by adding electrons as lone pairs. Okay. A lone pair is just a pair of electrons that's not involved in bonding. Hence, they're also often called non-bonding pairs, because they're a pair of electrons that don't take part in bonding. And again, you take off 2 electrons per lone pair. Any electrons that remain, there won't always be electrons left over, but if there are any electrons left over, you go ahead and you throw those on the core atom as more lone pairs. And again, you subtract 2 electrons per lone pair. If at that point your central atom does not yet have a full octet, then you go ahead and you turn lone pairs into double or triple bonds. So you take a lone pair from a satellite atom, you turn it into a new bond. This won't take any bonds or electrons out of your pool because you've already used them. These will just be a way to fill in the octet on the central atom. So let's go ahead and do some examples. So first up, let's do ammonia. Ammonia is NH3. So nitrogen has 5 valence electrons. There are 3 hydrogen atoms. Each hydrogen atom gives us 1 valence electron. So we have a total of 8 electrons in our pool. Now, when it comes to choosing the core atom is usually written first. It's usually more electronegative, and there's usually only one of it. Any and all of those rules can be broken, and are. But it's a good rule of thumb. It's just a general good way to judge which atom is going to be at the middle. Now, word to the wise. Hydrogen will never, ever be in the middle. Hydrogen can only ever form one bond. Hydrogen is, really quick, take this away. Hydrogen is on the first energy level. It only has access to that first energy level, meaning it only has access to the S sublevel of that first energy level. It can only ever have 2 electrons. It will never, ever go beyond that for any reason. Hydrogen will never be able to form multiple bonds. Therefore, hydrogen will never be in the middle. Okay. So for this one, nitrogen is our core, and it's going to have 3 satellites in the form of hydrogen. So we go ahead and we throw nitrogen in the middle, hydrogen, hydrogen, hydrogen. Okay. Now each of these lines represents a single bond, and each bond represents 2 electrons. So that means that in forming bonds with these 3 hydrogen atoms, we've got 2, 4, 6 electrons. Okay, so we've used up 6 of our 8. So we have 2 electrons left over. Now, hydrogen is one of the exceptions to the octet rule, and this is important. You need to remember this. Like I said, hydrogen will never go beyond those 2 electrons, meaning it does not get a full octet. So you're not going to put lone pairs around these hydrogens. Okay. If it were nitrogen trifluoride, if it had 3 fluorines instead of 3 hydrogens, that would be a different story. But hydrogen will never go beyond this. So you're not going to put lone pairs around hydrogen. Okay. Instead, the last 2 electrons will go on nitrogen as a lone pair. Okay. So that uses up our remaining 2 electrons, and we're down to 0. Now, do we need to do anything else in order to satisfy nitrogen? Does nitrogen have the full octet? Yes, it does. Because nitrogen looks around itself, nitrogen sees 2 electrons here, 2 electrons there, 2 electrons there, and 2 electrons there. 2 times 4 equals 8. Nitrogen is happy. Okay. So this is the Lewis structure for ammonia. Okay. It has a single bond to each of the 3 hydrogens, and it has a lone pair. Let's look at something a little bit different. Here we'll look at carbon tetraiodide. Why? Because it's different. All right, carbon tetraiodide, Ci4. You're going to focus in a second. I know you are. You're not an evil camera. You're a very kind camera. You're going to focus. There we go. All right. So carbon gives us 4 valence electrons. And then each of our iodines gives us 7 valence electrons. There's no charge on this, so we don't have to subtract anything. But 4 times 7 is 28. 28 plus 4 is 32 electrons. Now, once again, our central atom is going to be carbon. Carbon likes to go in the middle. Carbon is very much the mom of the group, taking care of everybody. So carbon goes in the middle. We surround it with our 4 iodines. And now we go ahead and we draw a single bond from carbon to each of the iodines. 1, 2, 3, 4. That uses up 8 of our electrons. We're down to 24. Then, I should have kept this sheet handy. There it is. Having drawn out the single bonds, we're going to go ahead and fill in the octets on the satellites. Iodine is going to want that octet. So, 2, 4, 6. We stop at 6 because it already had 2 from that single bond. So 2, 4, 6, 8. Okay. So we use up 6 for that iodine. 8, 10, 12, 14, 16, 18, 20, 22, 24. And now iodine is happy. Okay, all 4 of the iodines are happy. Each of them has a stable octet, and we've used up all of our electrons. So nothing is left to go on carbon at the middle. Are we going to need to make any double bonds in order to make carbon happy here? The answer is no, because carbon also has the full octet. It looks around itself, it sees 2 electrons there, 2 electrons there, 2 electrons there, and 2 electrons there. Carbon sees a total of 8 electrons. It's good to go. This is the Lewis structure for carbon tetraiodide. I've already mentioned carbon dioxide once, so let's go ahead and take a look at that. So carbon dioxide, CO2. Carbon gives us 4 electrons. Each of our oxygens gives us 6, for a total of 16 electrons. Once again, carbon is going to go in the middle. We're going to put oxygen on either side. Next up, we draw a single bond from carbon to each of our oxygens. 2 bonds, 2 electrons each. That uses up 4 of our electrons, leaving us with 12. Now, we fill in the octets on each of our oxygens with lone pairs. Each oxygen already has 2, so 2, 4, 6, 8, 2, 4, 6, 8, which means we've used up 2, 4, 6, 8, 10, 12 of our remaining electrons, and we're completely out of electrons. So there's nothing left to go on carbon as lone pairs. We've used up our pool, nothing left. But carbon is not yet happy. Carbon looks around itself and it sees only 4 electrons, 2 from either bond. Okay, so carbon, no bueno. So what we do now is we satisfy carbon's octet by turning lone pairs off of the oxygens into double or triple bonds. Now carbon is going to need 4 more electrons. That means it's going to need 2 bonds, 2 electrons per bond, right? So the oxygens are identical, so we just go ahead and take 1 pair of electrons off of there and 1 pair of electrons off of here. So now there are 2 double bonds. Okay. So these electrons didn't really disappear, they just got moved over here. Okay. So now each oxygen looks around itself, and each oxygen is still going to see 8 electrons. So 2, 4, 6, 8. So each of these lines represents a bond, and each bond represents 2 electrons. Likewise, this oxygen sees 2, 4, 6, 8 total electrons, and carbon likewise, 2, 4, 6, 8. Everyone has a stable octet. Everyone is happy. You can get more complicated structures than this. I've already mentioned one exception to the octet rule, and that was hydrogen. Hydrogen has an unfilled octet, okay, meaning it only goes up to 2. There are two other ways you can get exceptions to the octet rule. The first exception I'm certain you need to know is boron. Let's look at the ever popular boron trifluoride. Focus for me, baby. There you go. All right. So boron, element number 5, gives us 3 valence electrons. Each of our fluorines gives us 7 for a total of 24. So we're looking at a pool of 24 electrons. Boron goes in the middle. Then we surround it with our fluorines. Now we're going to go ahead and throw a single bond onto each of those fluorines. So 1, 2, 3. 3 bonds, 2 electrons each. That uses up 6 of our electrons, leaving us with 18. Now we fill in the octets on the fluorines with lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That uses up all 18 of our remaining electrons, leaving us with 0. So nothing to go on boron as a lone pair. Now, you would expect that you would then go ahead and turn one of these into a double bond, but that would be wrong. No, 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 no. Don't do that. Bad chemistry, student. Because, like I said, boron is an exception. Boron is happy to stop at 6 electrons. Boron is just weird that way. Okay. It will go on to 8 if it has to, if you give it the opportunity, I guess. But the fact is that these fluorines are perfectly happy to stay right where they are and not donate a lone pair to form a double bond. And boron isn't going to push the issue. So boron will stop here with a total of 6 electrons. It is happy with that unfilled octet. So that is the second exception that you need to know. First up, hydrogen only ever goes to 2. Boron is happy to stop at 6. Okay. So let's go ahead and look at the other exception, the third and final exception, which is a much broader exception because it is a class of exceptions. Okay. Let's look at sulfur hexafluoride. Sulfur hexafluoride is one of my favorite examples for reasons we'll get to in a minute. First up, sulfur gives us 6 valence electrons. Then we have 6 fluorines, each of which gives us 7, for a total of 48. So, sulfur is going to go in the middle. We're going to surround it with fluorines. And now we are going to draw a single bond from sulfur to each of our fluorines. 2, 4, 6, 8, 10, and 12. So that uses up 12 of our electrons, and we're left with 36. Then we slap lone pairs on our fluorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. That uses up all 36 of our remaining electrons. No lone pairs on sulfur. Are we going to need to make a double bond for sulfur? Well, how many electrons does sulfur see around it? 2, 4, 6, 8, 10, 12. Sulfur has 12 electrons. Doop. That is more than 8. Sulfur is overflowing with electrons. Sulfur has what is known as an expanded octet. That is to say, it has more than 12 electrons. Okay. That is perfectly fine. That is an entirely reasonable thing to do because let's go ahead and look at the periodic table. Here's sulfur over on the 3rd row. What does the third row have that the second row doesn't? It has these guys. It has the d orbitals. Empty d orbitals, just waiting for electrons. So the third row has those, the second row doesn't. Likewise, the fourth row is going to have an empty d orbitals. Fifth row, sixth row, all have empty d orbitals just waiting for electrons. So for any element, third row or below, you can have an expanded octet. You cannot do that for these guys up here. They will never, ever go beyond 8. In fact, and like I said, hydrogen can't even go beyond 2. Okay? So the second row can only go up to 8. The third row and beyond can go beyond 8. Excuse me. All right. So expanded octet, third row and below, never beyond that. Never above that, I should say. Second row, only 8. First row, only 2. All right. Now, Lewis structures handle lots of different things in lots of different ways. Let's look at what's called a polyatomic ion. Specifically, let's go ahead and look at carbonate. CO3 2-. If any of you is a big fan of baking, you'll be familiar with carbonate because it is part of baking soda. Sodium bicarbonate, in fact, NaHCO3. All right, so carbon gives us 4. Our 3 oxygens give us 6 each. And then we finally have a charge of -2. Okay, so we subtract that charge. That -2 charge means we have 2 extra electrons. So 18 plus 4 is 22 plus 2. We have 24 electrons to play with. So once again, carbon goes in the middle, and we surround it with oxygens. We draw a single bond from each of our oxygens to carbon. 3 bonds, 2 electrons each. We use up 6 of our electrons. We're left with 18. Now we're going to go ahead and fill in the octet on each of our oxygens with lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18. That uses up the last of our electrons. No lone pairs for carbon. But carbon is not yet happy. Carbon only has 6 electrons, 2, 4, 6. 1, 2 for each bond. So that means that we're going to have to make a double bond. So let's go ahead and grab a lone pair off of this here oxygen, turn it into a double bond. Now everybody's happy. Each of our oxygens looks around itself, sees 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and carbon sees 2, 4, 6, and 8. Everybody's happy. But we're not quite done. Because, as I said, this is an ion. It has a charge. We always have to indicate that there's a charge, and we do that with our brackets. We put the charge outside of them to indicate that the charge is on the entire molecule, not just on one part of the molecule. Oops, square bracket. There we go. All right, so that is carbonate. Okay. You can get a combination of double bonds and lone pairs on the central atom. That's not a problem. You can get an expanded octet with lone pairs and, I suppose, double bonds if you had to. I can't think of any examples off the top of my head, and I'm not going to try because I'd screw it up. But you could. Now, one last thing. Resonance. Okay. I didn't mention the term in my lectures, but resonance happens with degeneracy. It also happens here. Basically, this oxygen is not in any way different from this oxygen or this oxygen. So there's no reason to put the double bond here as opposed to here or here. And the thing about electrons is if electrons can exist in more than one location, then they do exist in more than one location. You walk into a room, there are 5 chairs, you sit in one of the chairs, and that's it. An electron walks into a room, it sees 5 chairs, it sits in all 5 chairs at the same time. That's resonance. So this double bond is not just here. It's also down here and over here. And it exists in all 3 places at the same time. It exists in all 3 places entirely equally at the same time. It is not bouncing around between the 3 locations. It's not here or here or here. Instead, it is here and here and here, all at the same time. Okay? We have ways of measuring these things, and when we look at carbonate, we do not see a double bond and 2 single bonds. If we did, we would see, 2 different signals. 1 of these and 2 of these. Instead, we see 3 bonds that are all exactly the same. All of them partway between being a single bond and being a double bond, because that double bond exists in all 3 places at the same time. So here's how we show that when we draw it out. Here's how we represent resonance. Okay. So carbon, oxygen, 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 double, single, single, dot, 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 bracket. So that is the first of what we call our resonance structures, with the double bond up at the top. Then we draw the second one. Carbon, oxygen, oxygen, oxygen. Now we draw the double bond in a different location. And then we fill in our octets. Oopsie. That double bond shouldn't there. Yeah. I drew too many electrons. All right. And then we bracket it and double and 2 minus. So that is the second of our resonance structures. And then we draw our third one down here. Carbon, oxygen, oxygen, oxygen. Double bond in the last of our 3 locations. We fill in our octets. We put in the bracket, 2 minus, and we draw our little arrow. And that right there is how we draw carbonate. We have to, if we want to include the full picture, the full structure of what carbonate is, we have to include all 3 of these pictures, because no individual picture is true by itself. You have to have all 3 or it's no good. Now, resonance can only happen if you have double or triple bonds. It won't happen otherwise. If you only have single bonds, no resonance. It can get a little bit more complicated than that, but that is going to be your first really big clue when you're drawing Lewis structures. If you have a double bond and it can go in multiple locations, if there's no difference between them, then it is in both of those locations at the same time, or all 3, or all 4. Resonance pictures can get quite big. Resonance plays a really, really big role, because resonance means stability. Electrons like being able to exist in multiple locations. Electrons like being able to spread out. It makes them happy, having more room, having a bigger apartment, So that is why carbonate, that's one of the reasons carbonate exists. It's more stable. It's a happier molecule. But this also has an impact on a lot of things. For example, a big thing in organic and biochemistry are carboxylic acids. A carboxylic acid, for example, here's a simple one you probably have some experience with. This is an example of an extended Lewis structure, okay, where we have multiple centers. That's not a problem. We just take the same sort of principles and expand upon them. They will, in fact, ask you to do that for this lab, and I think they might ask you to do that on the test. But we see here carbon with its full octet, and then each of these hydrogens is happy with just 2 electrons. This hydrogen over here is happy with just 2 electrons. This oxygen has the full octet, 2 and 4 from the bonds, 6 and 8 from the lone pairs. This oxygen has 1, 2, 2, 4, 6, 8, I should say, electrons. And this carbon, 2, 4, 6, 8. So everybody's happy. This right here is known as acetic acid, more commonly called vinegar. Okay. The reason it's an acid is because of this guy. That is an acidic proton, as we call it, because it can pop off as H+. And it'll leave the rest of the molecule behind, looking like this. When that happens, it will be, I'll go ahead and abbreviate this as H3C, because you have 3 hydrogens bound to that one carbon, then carbon, double bonded to oxygen, single bound to oxygen. This oxygen still has 2 lone pairs, but now this guy has 2, 4, 6. That hydrogen didn't take any electrons with it. It left the electrons in the bond behind. So now this oxygen has 3 lone pairs, and this is now an anion. And the reason it's able to do this is because now we have 2 oxygens, and there's no longer any difference between them. Before, there was the difference. This one had an oxygen, or this one had a hydrogen bound to it. Now, there's no difference. So this this double bond up here is now free to resonate back and forth between those 2 oxygens. That stabilizes this ion, and that's why this proton is able to be acidic. So this is a whole class of compounds. You end up with this resonance structure, so H3C, single bound to O, and then double bound to this O. Okay. So that's the resonance. All right. So like I said, this is a whole class of structure called carboxylic acids. And this acidic behavior is vital, not only because you get lots of acids like these. You also have, for example, formic acid is a carboxylic acid, and it's why ant bites sting. It's called formic acid because in French, possibly also in Latin, the word for ant is fourmi. So that's where formic acid comes from. Or at least that's where the name comes from, because ants have it, and ants are for me. So formic acid. These carboxylic acids, they all have very strong odors, like vinegar do. And they're responsible for why sweat stinks, because you got carboxylic acids in your sweat. They're very, very important in all sorts of biology. They're vital to proteins. The reason proteins, you might remember, are made of amino acids. The amino comes from ammonia. The acid part comes from a carboxylic acid on the other end. The reason proteins have much of their functionality comes from the fact that they load their functional centers with carboxylic acid groups. They're very important. They're vital to biochemistry. And they also play a lot of significant roles in organic chemistry, making drugs, legal drugs, and I suppose illegal drugs as well. So all sorts of things. They're just absolutely vital. You find them everywhere, in nature, in medicine, in industry, incredibly important. And the reason that they are acids at all is because of this resonance. Okay, so resonance is incredibly important moving forward. It explains a lot of chemical behaviors. So really important if you continue studying chemistry, and even if you don't, it'll be important on the test. So remember that. Keep an eye out for double bonds that are able to exist in multiple locations. Now, let's see if there's anything else in this lab you'll need me to discuss. No, that's everything. All right. Good luck this week. I will see you around. I'll hang on a few seconds to see if you have any questions. There's no one here, so